don't know if you had any questions on the three-level part, okay? So this is considered, of course, the easiest part and most powerful part, okay? The amplitude methods, on-shell methods are very powerful for this three-level. As I hope if you were lost in some details, at least hope you got the flavor that this is very powerful technique, okay? To understand many things that are hard to understand or harder to understand from Lagrangians, okay? At least this to motivate you to read many other reviews and that you will find in the literature. There are many beautiful reviews, okay? Because the part that is more difficult is when we go to loops, and of course, now nature is quantum, and we have to do loops, and there the things are not so clean, okay? So and what happened is we don't have a systematic way to get loops, okay? You learn, it took you probably 1 or 2 years to learn really quantum field theory, how to calculate first Lagrangian and after that amplitudes and how to calculate one loop. From the Feynman diagram, you can calculate 3 levels, 1 loop, 2 loops, okay? It's difficult, but you know how to do it, okay? There is a systematic way to do it, and here we don't have a systematic way, okay? So my point here is going to tell you how to do something renormalized at 1 loop, and you will see the kind of difficulties and how people are doing it, okay? Because let me say something, even though you think we don't have systematic way, most of the people doing higher loops go through these methods, okay? Because when you go to many loops, with Feynman diagram, you have so many diagrams that you cannot even calculate, that people are using these methods, even that is more, you have to find a way to do it, okay? So there's no systematic way, you have to learn how you can do it, but this is what people are using. And in fact, if you see these papers calculating at 5 loops supergravity theories, the calculation of 5 loops, 6 loops, they want to know if it's finite theories or not finite, okay? You get infinites or not, because there claim to be some supergravity theories finite, they use these methods, okay? So I'll flash how people do at the 1 loop level, okay? I'll get it to the 1 loop level, and I will try to calculate or to show how to calculate what Rodrigo was telling you, the anomalous dimension, the divergence of a diagram that you have to reabsorb in your coupling. You already realize I have also couplings or coefficients and knowns, okay? In front of my amplitude, I have to put to have a coupling, a gauge coupling, or sometimes Wilson coefficient, we call it, okay? These are coupling that you don't know what they are, and you can redefine, renormalize them, eating the infinites that you find. Okay, so this is very similar to what you do in quantum field theory, okay? Now the motivation is a little bit the motivation that Rodrigo mentions, okay? I want to say why it's useful, because you get more information, and one of the information I want to show is when you renormalize, okay, using a little bit of Rodrigo, when you have operator mixing, okay? You have some dimension 6 operator that mix with another one, and this is very important when we do phenomenology, okay? Because, for example, we measure something very well like electric dipole moment, okay? And we want to know if we could put a bound from 4 fermion interactions, okay? We want to put a bound on this, okay? And of course, we can measure really fermion going to fermion, but I better, you can close a loop, okay, and generate what is called this higher dimension operator, fermion, W Higgs. When the Higgs gets a BEV, can give you dipole, okay? And now, for example, if it's complex, okay, we have a very good measure of electric dipole moments, so it's better to put a bound on this operator, or try to see the physics from this operator in the electric dipole moment, that is this diagram here, than by taking the 3-level part. It will be fermion, because we don't measure so accurately as we measure this electric dipole moment, okay? So the operator mixing is important, okay? To know how this 4 fermion interaction generates another fermion. Okay, this is in my language. Okay, in the language of operator, this will be psi gamma mu psi square. Okay, and this will be the operator with two fermions. That is a dipole operator. Okay, that is in operator is the operator psi bar sigma mu nu psi h f mu nu. Okay, you generate this operator. Okay, that is when the Higgs zeta Bev can give you, if you have an imaginary part in the coefficients and the contribution, electric dipole moment. Now, if you calculate this one of the diagram, when you calculate the divergent part, you get 0. Okay, if you look for the divergent part, there's some finite Pearson on 0, you get 0, and it's difficult to understand why. This is one of the examples that I'll try to show you that there is no divergence. Another one is like this one, you can calculate. Okay, so this will be a little bit the motivation that, at least to me, bring me to look at it in this way. Also, if you calculate this contribution, this operator is one of the operators, two fermions and two Higgs. Okay, you can also a priori contribute to something like looks like the dipole. Okay, but again, this is the divergent part is 0. There's no symmetry, nothing. I don't understand. I have to put, this is one loop Feynman diagram. There are more loops Feynman diagram. I add all of them and I get zeros. And there are other examples that are like this, okay? So this motivates a little bit to understand it in the on-shell methods, okay? But we will try now to see. Okay, so let me understand how I can do the loop level. Okay, so a priori it looks like, okay, I have to calculate the amplitude, okay, at the loop level. Okay, so it will be an amplitude where something like this, okay, generically will be some higher dimension operator inserted here, and you already showed, Rodrigo was showing another example. Okay, so you can have many, okay, schematically it will be something like this. Any other higher dimension operator can generate an amplitude like this at the loop level. Okay, and trying to see how I can find this amplitude. Okay, when I know a calculation here is not, the states are not on shell. Okay, of course, you cannot calculate, you calculate these guys off shell. Okay, and the strength of my method is to go on shell. Only the physical states. When you know here, there can be unphysical states when you propagate H boson. Okay, now any loop contribution can be splitted. Let me say a little bit to see how it goes. Okay, you can split it as a function of what is called the Passarino-Bellman expansion. Okay, let me say C2A, C3. You see, you have to see how the loops are to try to get them from on-shell amplitudes. Okay, so the loop level, you can always expand this in these I's that are integrals. This is called the Passarino-Bellman expansion. This is the dimension, so, and as Rodrigo was telling you, I'm following also dimensional regularization. So I'm not calculating. I know it can be written like this, okay? Of course, I can calculate it, but right now I use it, and I want to use only the property. This can be written like this. Okay, so up to, because I don't have a space, up to okay, so any of these Okay, I can split this integral. I know I can do it like this. Will be coefficients that are the one that I have to get from the calculations. Okay, this is the information I can only get from calculation as a function of some integrals, okay? That I divide by I2, I3, I4, because these are integrals involving 2 propagators, 3 propagators, and 4 propagators, okay? So this I2 is, on the formula upstairs, something that has like this, okay? Something like 2 propagators. This I3 has like can be decomposed like this when can be many legs here, okay? There are 3 propagators or 4 propagators, okay? I can always reduce my couplings like, let me count the number of legs to be 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. Sorry, so here I need to keep, okay, this is for any one, okay, I just chose this two. So 1, 2, 3, 4, 5, 6, okay? So this can be done, plus something that has nothing to do with integrals are called rational terms. That are polynomials in momenta, has no, okay, some remnant parts that I cannot write it in this way, okay, but are polynomials, okay? So this is a basis, if you want, of integrals. And as I said, the important thing of the loop, the calculation that you do is these coefficients, okay? So I know I can do this expansion, and I want to calculate these coefficients. I would like to calculate these coefficients in the on-shell method, okay? Now, the most important thing is the divergent part. This diagram, Rodrigo told you, diverges sometimes, and this is important because they want that you have to reabsorb in the tree-level part, okay? This has to be, the divergence has to reabsorb in some coefficients of your theory, and this is what defines your anomalous dimension, he was mentioning, okay? So, if, okay, question is what I'll do is to try to look for this part of the divergence, but I'll flash you how it goes if you want to calculate the rest, okay? The idea is what I can do here. Well, the idea is to cut this diagram, what it means cutting this diagram, okay? And I'll tell you what is cutting, okay? But what in the books of quantum field theory means cutting the diagram, that means putting 2 states on shell, okay? So the idea is to cut the diagram, but we'll be cutting the diagram here, we'll be cutting the diagram also here, okay? Cutting the diagram, okay? Sorry, I lost my electronic pen, so I had to write it in the... No, I'm using just that know that this can be written like this. Any loop, I don't do calculation. I don't do jet calculation. I only know the loop calculation can be written like this. Okay? If I want to calculate the C's, I have to go to the Lagrangian and calculate them as Rodrigo was doing. Okay? This in fact has nothing to do with, this only has to do with the fact that they are here propagated or whatever you can show. This is an easy way to show why you can always expand this, but take it for granted. Yeah, this is like this. Okay. Okay, cutting means that wherever you have a propagator, you put the propagator on shell. You get the part of the propagator where the p square goes to m square. Okay, this is the imaginary part of this. Okay. Okay, this is the imaginary part of things. So cutting means this, putting the propagator on shell. Okay. And you already know that these tricks have been done. I have seen it, I remember Brando, we already used it because he was looking at some point to the imaginary part of this diagram and he said, okay, this is you can get it from cutting here. So it's related with the optical theorem. Okay, this is why the methods that I will use sometime are called generalized unitarity methods. In some sense, it's a kind of extension of the optical theorem, okay, that, for example, tells you that the imaginary part of this M, of this process here, okay, as probably you know, is coming from cutting this diagram, okay, where you have, okay, you have to, when you cut the diagram and you put these guys on shell, it is exactly the contribution that we are looking for. It's exactly a three-level contribution integrated over phase space, multiplying another three-level contribution. Okay, it looks like something like P1, P2, D3, okay, no 4, P1, 2A1, you can put the pi's, 2 pi 3, 1 over 2, A1, and integrated dp over the momentum, 3 momentum, so it's a phase space integration over the amplitude A going to BC, okay, if I call this guy A, and this guy going to BC, okay, 1 times the complex conjugate of the other one. Or you can call it B going to BC going to A. It's the same, ABC, A going to B, C, complex conjugate, okay? This is what we are looking for, okay? This is the idea behind, okay? This is a loop calculation, but you can get the imaginary part, okay? Not the full thing, but when you have the imaginary part, okay, you have a lot, okay? Because we know complex, the analysis tells you with the imaginary part, sometimes you can even get the real, okay? But we will see what we're going to, okay? But I mean, at least the imaginary part of this diagram, I can get it from three-level things, okay? But with an integration over phase space, okay? This give me the width, okay? This is what Brando was using to tell you this is proportional to the width, okay? Okay, that is positive. I was using the positivity relation for something else in his analysis, okay? So this is the idea people have, okay? And is in the much better discussed in the, longer discussed in the first paper I put you the first day of Lance Dixon, okay? There you will see, you look for generalized unitarity and tells you this, okay? I'm going to look for the imaginary part, okay? So what is the key point? If I look for the imaginary part here, I will get the imaginary part here. And in fact, the imaginary part I'm looking is only in this diagram, okay? So because this, I know what it is, okay? So getting here the imaginary part, okay? Or equivalently, by looking when these two of the propagators here goes online, on shell, online, shell, okay? Delta P square M square, okay? So when this integral I go on shell, okay, I'll get the imaginary part, okay? So I equate the imaginary part here with the imaginary part here, and in this way I want to get this coefficient in front, okay? I know what is the imaginary part of these integrals. They're here upstairs, I have to calculate them, okay? And I'll get this way the coefficients, okay? This is the way I'm going to do, but people have been sophisticated enough to, okay, because there I know by 2 cuts I get the coefficient. I will tell you why. When I am tested only in this guy. People have elaborated these methods beyond this thing, okay? This imaginary part is related only when you do 2 cuts, and people have been looking, okay? Because with 2 cuts I only get information of this. In order to get information of this, for example, this coefficient, people have thought, well, just still 4 cuts here. If you cut 4 lines here, okay, means in 4 lines where you have this, you put this. You see here, there is no 4 lines. The contribution can be 0, 0. It will be equivalent to cutting 4 lines here. Okay, and now I can have a relation between this amplitude this contribution, okay, when I cut 4 lines, is easy because I put in the particles on shell. So is this process amplitude on shell times this amplitude on shell times this amplitude on shell times this amplitude on shell integrated over some phase space, okay? I have to put this on shell. You can do it going to the complex plane only of the momenta. So this contribution I can do on shell will be giving me information about this C4 because nothing appears from here or here. This is the idea of generalized unitarity methods, okay? I start looking how cutting lines, okay, it's the art of cutting, okay? I cut 4, if I cut 4, only here I can generate and I can equate this with this coefficient C4. And I have different cuts to get the different coefficient because I have sum over C because there are different types of fine integrals here. I can have a particle, I can have different particles coming in the different vertices, okay? There are different types of these boxes. These are called boxes, okay? Boxes, triangles, and bubbles, okay? And this is the method, okay? So for 4 cuts, I can relate it and I get this information. Because when I do 4 cuts here, I do this operation on this integral, I know what it is, I get something, so I know what is this result, so I get information on C4. Okay, when I calculate all C4, okay, I do 3 cuts. Okay, second step, I do 3 cuts, 1, 2, 3. Okay, doing 3 cuts, this is still does not appear, but now it appears this. Okay, so I get information of this, which is also of course, I will have information on this, but already I fixed this one, so I'll get information about the next ones. Okay, these are already known from the 4 cuts. 3 cuts will give me information of that, and I go down to 2 cuts and I get all the information. Okay, so this is the techniques I will not explore more, but people are doing in order to get the coefficients. Okay, relating with something amplitude at this loop level. This is the point now where I did the cuts, and it's just cuts mean put it on shell, and this is what I want. And now this is a combination of on-shell amplitudes. Okay. I'm going to do it only for the 2 cut, because I'm looking for the divergent part. I want to understand why this thing is 0, why this thing is 0, okay? But I'm saying this method extends in this way. The difficult task, okay, so I don't know if you understand the logic, more or less the logic, okay? Because the details are a little bit elaborated because you have to calculate these integrals when you put 3 of their propagators on shell, and to relate really these guys with these guys, okay? So there is, you have to do systematic here, but there is a systematic way of getting this coefficient of this coefficient from things on shell, okay? This is a trick, but that's the trick we had to use. The big deal, the big guy, big elephant in the room is this guy, has rational term, is a polynomial, okay? And this is it's a beast, okay? To get, I don't want to enter into it, okay? So, okay, this rational term, these things that cannot written like this, yeah, are difficult. There are techniques, other techniques I want not to develop, okay? I don't want to talk about, okay? Because it requires more time. You have to, okay. But you see the way, there is no Feynman way to proceed. We have to proceed in finding tricks to relate this with this, okay? And the information only used here is that I can write this thing like that. Okay, but loops give me this, okay? So formally I write it like this, even that I don't know what are the coefficients, I get the coefficient. Okay, so let me do it for a 2 cut. Okay, and I'm interested now in renormalization. Okay, but I'm interested, okay, let me go for example, one example, to make it clear what I'm looking for is this anomalous dimensions that we are getting at 0. And I'll tell you how the formula goes, and of course the detail. Other people did the same. Okay, hope it's okay. Okay, yeah. Oh, it's really late. Okay, so my interest would be, I was saying, Okay, let me still continue with this. 1, 2, 3, 4, 5, 6, okay, where I am doing something like this. I put a higher dimensional operator, or in other words, in my language, it's not a higher dimensional operator. This is just the amplitude that goes like 1 over lambda squared, okay? It's an amplitude that goes like 1 over squared, okay? That's the one. That give me another amplitude where the external legs are different, okay? Give me an amplitude that instead of 2 fermions and 2 Higgs, I have 2 fermions, Higgs, and another, okay? So Rodrigo was talking about operator mixing. I can call amplitude mixing. Okay, I have some amplitude that now can generate at the loop level. Other type of amplitude I had can be divergent, and now I have to reabsorb it from my coefficients. Okay. And the question is, okay, I'm interested. So there is some amplitude 1 over lambda square here, and I'm interested only in the 2 cuts. That is this easy part, because this is I can use this imaginary part here. Okay, and I cannot, and it's easy to show in this case. Of course, I have to do 2 cuts everywhere, but something surprising happened is that the divergent part is here, as you can see. Okay, I'm interested in this coefficient because this is the only one. Okay, I2 is the only one you be divergent. Okay, because the one you integrate d4, d is equal 4, these are dimensions, okay, of 4 plus epsilon, d4. You have 2 propagators, so you have 4 momenta upstairs, 4 momentum downstairs, is logarithmically divergent. This is the one that Rodrigo was talking, there is logarithmic divergences. Okay, this is one of these guys. Here you have 3 propagators downstairs, this is finite and finite, okay? So this is the only one I'm interested, and when I do the cuts, okay, this is probably not easy to see, but the contribution of the total of this thing, okay, this is I have to tell you what happened in this situation, that the 2 cuts give you 0, okay, these add to 0. In the case I'm looking for, okay, in special cases, not always give you 0, okay, in the 2 cuts. But in the cases I'm interested, okay, when I'm looking for mixing of amplitude to the other, there is a problem here, the amplitude that has to do with infrared divergences, okay? So here it comes all the details, okay, that I don't want to enter because I'm interested, there is no infrared divergence when I'm interested in this type of diagrams. It is the mixture from one operator, how one operator enter into the other, one amplitude enter into the other, okay? So only, you can make it clear, only in this case, this is 0, okay? When no infrared divergences. Okay. This can be shown that in this case you can relate it with this. Okay. Also you can relate it by imaginary part, or you can relate it by just plugging here what I had there, the delta function here and here, delta function here and here, and this will give me a number. Okay. And now I equate this and this, I will get information on C2. Okay, on the divergent part, okay? Yes. Sorry? I5? No, there is only I2, I3, and I4, no more. Only you can write it, it can be shown, can only write in integral, they go with, where you have here, okay, you see, 4 of them. Eh? Eh? So this is for any external particle, 1 loop. This is only 1 loop. I can only, this is the Pastorino-Bellman, this is that you can expand it in this. Only integrals of this type appear in the 1 loop. Only integrals of this type appear. No more. So the idea at the end is that those, okay, let me write the formula because as you can see, there are a lot of details, okay? So this is the idea, and now the details you have to put yourself, because you see, cutting here will mean, cutting, I put these particles on shells, so this is a 3-level amplitude, and on the other side, I have 3-level amplitudes, okay? This I can call it, as I was calling the other day, A left amplitude here, A right amplitude here. I'm putting there on shell, putting the deltas there. You see that the integral here become a phase space integration as the same I was showing in the example, okay? So this is just a product of 2-3 level amplitude with an integrated over the equivalent things of here, okay? Integrated over the phase space, okay? In fact, let me write the formula you get, okay? So I'm interested in amplitude, I call it J, that renormalize, okay? Enter into an amplitude, normalize the amplitude I, okay? So the gamma, that is the anomalous dimension, is that coefficient that was Rodrigo talking, okay? Of this amplitude A, okay? I'm talking about dimension 6 operators, okay? So this amplitude are of order where I could put it. I could put it up here, is of order lambda, 1 over lambda, okay, or of order lambda square. I don't know where I should put it. Okay, I don't put it anywhere. Okay, dimension 6 operator. Sometimes I put BSN. Okay, this is a dimension beyond the standard model, dimension 6. Okay. Okay, I can write the next formula. Okay, I'll write it, although will not mean much to you. These are the coefficient, Wilson coefficient that appear in front of them, just to see what it comes up. Something that we call the ellipse, sum over, and we will see the example. This is the, okay, so my idea is how this amplitude enter one loop and generate this one, okay? How this amplitude, dimension 6, okay? 1 over lambda square amplitude affect this one, okay? And I'm telling you that you can write it like the anomalous dimension, okay, that give me the mixing, the same as Rodrigo defined, okay? I'm skipping here, okay? You can calculate, fulfill this formula. You can calculate it over integrate of the ellipse. This is Lorentz invariant phase space, okay? It's a phase space integration. Yeah, probably, I don't know if this formula is useful. Okay, okay, I'll finish it up because I started, because I'll go to the example. Probably it's just to see how it goes, times another standard model amplitude, okay? Sorry, this is taking in the third paper I gave you the first day, this is defined and how it is exactly found, okay? The key point is that this thing is, the idea is that what I gave to you, okay? But this coefficient here, when you cut two diagrams, I only pick up this part. This is the only part, divergent part. So this is the anomalous dimension is related with this guy, and this is the guy I want to get, okay? So I cut here, I know what it is. This I don't know, but if I calculate this, I will relate with this. The other guys are 0. Okay, if I do it that, I'm putting all the factors and things, I get this integration of two amplitudes. Okay, and I'll put you an example because to see it, okay? On there, what does it mean, okay? This is a phase space integration. And now the means here, external legs and L1, L2, the sigma is some coefficients. Okay, I don't know if it's important. You have to put 1/2 for identical particles. These are details, okay, like you do when you do Feynman. It's full of details, as Rodrigo was telling you today, okay? You have, and I think you get the factor E and F that we were discussing the other day because of my notation, okay, where NF is number of internal fermions. Okay. This is the generic formula. I don't know if I put everything, but let me see it in detail. Okay, let me see it in example. Okay, that example there. Okay, let me take that example. Okay, the loop is this one. But this formula is telling me that calculate the anomalous dimension of this amplitude I. Okay, so the anomalous dimension of the amplitude that is vector Higgs fermion. Okay, generated by subamplitude that contains 4 fermions. Okay, Rodrigo was showing different types. Okay, I'm not going to the standard model because I want to see this zero. Okay, the mixing of this thing, the anomalous dimension will come from integrating two amplitudes, okay, or equivalently, you get here and you cut 2 lines, okay? Okay. For example, I put on shell these 2 lines, okay? Okay, what I have to calculate, so when I cut it, okay, this will be what I call the ABSM, amplitude, or left or right, okay, up and down now. And this will be the standard model. As you see upstairs, there is a standard model amplitude. Does not involve any higher dimension operator. Down here, I have like what I call BSM. Involve, okay, a blob means that there is an amplitude that goes like 1 over lambda squared. Okay, I call it BSM. Okay, this is the BSMJ. Okay, this part, and I have to, idea is I have to take this amplitude and integrate over, okay? The anomalous dimension, let me now sloppily rewrite it as integration phase space, the ellipse, Lorentz invariant phase space integration of this A BSM A standard model, okay? And now, okay? I'm not going to give the details because I have to show this is 0, okay? But this is the point. I cut this thing, I have this 2 and 2. Now, why this is 0? Well, now it's very easy to see what could happen. Okay, it could be 0 if one of these amplitude is 0. Okay, let me put the elicities now, very important. I'm calculating this guy with these elicities. This is the dipole. Okay, this is the dipole here. And you take the dipole operator and you calculate what amplitude you get out of it. Is an amplitude that has the 3, is one what I called before. There was an amplitude like this, okay, that had this, that had the minus, minus, minus in my theory, okay? Okay, it was the, or I can say when it was, we're calculating the loop of minus, minus, minus. We're calculating the loop of this one that can be written in my language like 3-1. I wrote it to you, 3-1, 3-2, 1 over lambda squared. We want to see the renormalization. The one loop appear here, induced by this guy. Okay, induced by this guy. That is a minus, minus, minus. Sorry, minus, minus. Sorry, yeah, I jumped over. I want to see is the relative with this operator when I project into, okay. When I project in alicities is a minus, minus, plus, plus. I have to see, okay. Okay. Okay, this is an amplitude that I had, that the loop level potentially can generate this amplitude. Okay, this amplitude. Now, I managed to split it to say the calculation, this anomalous dimension is proportional to integration of phase space of this product of on-shell amplitude. This I put it to you, as one of the amplitude I put it to you, and now it is this is a standard model amplitude. Okay, of 2 fermion, if this goes plus, This should go minus. Helicity is like this. Okay. And what we have here? Well, this is an amplitude of the standard model with all guys minus. Okay. And what we can use is that property I told you the previous hour. Okay. Standard model all, okay, in the standard model. Okay, total for PT have lambda total okay, with one exception. So you see now, we understand why we're getting zeros. We need an amplitude that doesn't exist in the standard model, okay? We managed to write the loop as product of three-level amplitudes, okay? It's a kind of a mechanic here. I have to get my amplitude I already calculated. This is why everything recycle on shell methods. First, I have to know all my amplitude at three-level. That's easy, it's done. Okay, when I have them, I loops, for example, on a Morse dimension, I have to take this one, and integrate, if you want, exactly with all the details, the formula is there. Okay, I have to calculate it. It is a ratio of coefficient, Wilson coefficients, of the amplitude I and amplitude J, the dimension. I think it doesn't matter this. It's just to say that there is an exact formula that you can calculate. The idea, I try to give it to you, okay, that at the end of the day is a convoluted product of these two amplitudes convoluted with the phase space integration, okay? And only to see that only if you look at the helicity selection rules, okay, I need an amplitude that has minus minus, okay, so this amplitude is zero, okay? This amplitude is zero. Anomalous dimension is zero, okay? Very good. There is something subtle, yes, there is not much cut. It could be a cut. Now I wanted to explain it, but I was not explaining. The question you could ask is, probably here's the good, what other cuts I have also this cut here, like this, no? Okay? Yeah, these cuts always give zero, because the bubbles, you see the bubbles, okay, I'm trying to get the coefficients, and the bubbles are these guys with two propagators, okay? So if I have a bubble with only one leg here, let's say many legs here, okay? It could look like this one. I have only one leg, okay? So I want to cut, okay? If you do this cut, we'll be cutting on the other side a bubble with one leg, external leg only, okay? I'm trying to say this type of integrals, I2, okay, where only I have one leg is called massless bubbles, okay, you can show these are zero, okay, because there is no, the p squared, these are massless particles, p squared is zero, okay, so there is no momenta here, there is no invariant. This cannot depend on any invariance. Okay? I have to distribute it out such that you see there is no, to say when you do the integral. These are called massless bubbles. Okay, these are called massless bubbles. So I have to have at least two legs here and two legs here. Otherwise, when I do the cut of one of those with one leg, okay, these amplitudes these integrals are zero, okay. This is a so I'm saying that what depends this thing depends on what depends on zero. There is nothing there to depend. Okay, there is not a variable to depend the integral. Okay, there is no S or T or U or P1 times P2. It's not dependence, okay? Yeah, there is this little detail that tells me, but important, that tells me the only cut has to be 2. I have to have on one side always two external legs, okay? So there is only this cut. Yeah, there's no more cuts. Yeah, I have to do all cuts. Yeah, I have to do 2 cuts. If I have more cuts, I have to be careful. Okay, but I can do it. Now, because of that, okay, I know I'm jumping over many details and things like that, okay, saying this can be well defined, okay, the idea is this one, okay, that's the trick to do it, and it's relatively simple because we already have to calculate 3 levels, the integral phase space. Loops becomes kind of trivial, okay, there is just a phase space integration, okay, that coefficient that usually hard to calculate becomes this, okay? You have to look this. It's a 0 when some of these guys are 0, okay? I can put another example. Well, here is the other example. I can go back here. These people also found was 0. And myself, I also calculate these things. I was getting a lot of zeros. This is why I was fascinated by this thing. I thought it was something deep I couldn't understand. In fact, I had an explanation by supersymmetry. Okay, so supersymmetry can help you. You see, I know it has nothing to do with supersymmetry, but we are using supersymmetry also to explain that some of the zeros. Okay, so I understand that it looks. Sometimes even that you don't have supersymmetry, you can use to organize your calculations. Okay. So if I have a calculation, a diagram like this, again, I can calculate the same thing, okay? It has to be the ellipse integration of some A DSM times A standard model, okay? And I have to cut, okay? The only cut is this one like this, okay? So this would be the A BSM, okay? Contains 1 over lambda square amplitude. And renormalize the other one. So this is just a standard model amplitude. You can see, as soon as you calculate all the standard model, you have the loops are coming easily. Take it, plug it, integrate over the phase space. Okay, so this is a kind of a process. It's a very physical process. 2 particles going, okay, to producing, rescattering to another ones. Okay, this is this process. They produce 2 particles, they produce this, and they rescatter like this. It's a physical. Okay, and you integrate, of course, over the phase space, all the possibilities here. And this is the sum here, I don't say. All the sum here, you don't understand. Yeah, probably I should not put it. All the sum here is that you have to sum over all internal possibilities. So I'm looking at the Feynman rules, but I should do it without looking even at Feynman rules. I have to look at here, okay, 2 external legs and 2 possible external legs, going to do rescattering and going to the final 2. Okay, so start with 2. Going to 2, okay, or 2 is 2, going to this to 2, okay, and doing like this without any looking for Feynman diagrams, okay. I'm doing it for Feynman diagram because now it's easy to tell you that in fact there is only one guy, okay, and this is this guy cutting here, okay, and now I have again the same thing. I'm calculating minus, 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 and this is a plus here. Okay, this is associated with the, okay, I'm interested in this amplitude in my case, is the one that people calculated was 0. Okay, but I can think this is just my amplitude, is the amplitude associated to the loop, to the operator that people calculated was 0. Okay. I take this minus plus plus again, I need here a minus. And now this amplitude is 0 again. Okay. So as soon as I put the amplitudes here that I require an amplitude with all minus, 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 will be 0 unless it enters the exception that I mentioned. Okay, but here I cannot enter the exception, okay, because I'm interested in going to a vector and a fermion, okay. Okay? And there are many of them. Okay, you can classify all these things. You know by looking at these things. Okay, and this is what explain it. Okay, this was, by the way, this was initially, didn't put it, this was initially done in the paper, as Rodrigo was mentioning, all the zeros, showing that this was zero, was originally the paper of Cliff, Chung, and Shen, 1505. Or 1844. Okay. This is the first paper I realized, look, if you use amplitude, you get a lot of zeros. Okay. In my paper that is related with the third reference I gave you the first day, okay, we rederived this thing, okay, we wrote this formula exact, because not only you get the zeros, you can also get the non-zero part. Okay, there are parts that are non-zero. You see, if I put here minus, okay, to say I can do zeros, and then you can look at many of them, okay. There is, for example, I have another examples, and you get selection rules. I don't want to enter more into details. Okay, this is another example that is zero. If you calculate an amplitude with 4 Higgs, and you want to calculate how you can generate the loop level, this amplitude with 4 Higgs can generate something that has 2 Higgs and 2 photons, something like this. Okay? 4 Higgs, okay, this is the 1 over lambda square amplitude. Okay, can you generate something like this? And again, this will come from this amplitude, and these are minus minus, okay? When to generate operator that is 2 Higgs, 2 photons, has to be minus minus always. Okay, and again, this amplitude, when I see this amplitude like this, it's a standard model amplitude, again, this is standard model amplitude that contains always minus minus is zero. Okay, so this no divergence part here, this anomalous dimension is zero. Okay, there are probably finite pieces. Okay, I'm talking not everything, I'm talking only divergent part, the anomalous dimension. Okay, there is no one amplitude that does not renormalize the other. Okay, can give a finite piece, that's true, not renormalization. Okay, I don't know. I could go on with other cases, probably to tell you that sometimes what I like sometimes to show that due to these techniques you see something that. I always like to put this example, okay, some cases that are non-zero, okay. For example, if now I tell you not this amplitude with minus minus plus plus, okay, but, okay, what I want to say is sometimes if you calculate, I like to say sometimes that for the case of that this is minus minus plus here, okay, this is not going to be, sorry, this is the case I had. Okay, this is the case I had, no? The case minus minus minus, okay, this is plus plus, and now this is not going to be zero. I have 4 minus here, I see that this amplitude really renormalized this one, because now I have an amplitude that is plus plus minus. In fact, this is the amplitude we calculated. Okay, 1 gauge boson, 2 fermions plus plus, the other minus, I think we calculated the conjugated, plus minus minus, but that is the same, conjugated, okay. This amplitude in the standard model is non-zero, we calculated. So there is a renormalization. If I plug the things, I can get it. But I wanted to show the recycling power is that this is very much related with something that doesn't look like from the point of view of Feynman diagrams, okay? If I tell you calculate without the cut, okay? If I tell you calculate this a la Feynman, and later I tell you calculate this a la Feynman, what you could do? Well, you will just calculate it. Okay? You will say, well, I calculate this, I cannot help, that will not help me at all to calculate this one. It looks, thermal particles are different, gauge boson things, okay, I don't think I can recycle anything. Okay? Looks like I have to start again and do, and this is what you do usually. You finish the loop, okay, now start the loop. This is what, I was also doing before, okay? Because now you do it on shell, now you know that this is going to be cutted. And two loop calculations that look very different. When I cut it, and I know I can calculate by looking at these two amplitudes integrating over the phase space, I see here it is not so different. Okay, what I have down here, okay, this is now the BSM part. Okay, this is the standard model amplitude. This is the BSM, I call BSM 1 over lambda square. This is the 1 over lambda square part. That is different than this. Okay. This is the standard model amplitude. But the standard model amplitude is the same, you see? It's a vector scalar fermion-fermion. Okay, vector scalar fermion-fermion. When you cut the diagram, you see, well, it's almost the same. Not exactly the same because what changes the operator of you're putting, the BSM part. But the standard model is the same. Okay? I have this calculation of the standard model, I can just plug it here and get the other. Okay. In some sense, the coefficient I calculate from the anomalous dimension here is related with the coefficient here. They have a relation. Okay. Because it will come from this part and this part. Okay. Of course, apart from the difference that this is a different amplitude, but that's okay. Okay, you're changing this guy. The difficult part is the integration over phase space, and the integration over space is easy. The difficult part is to calculate the standard model. Okay, I'm getting this part here is related with this. It may appear the same guy. Okay, when you cut it, you see it's the same. Okay, and you get a relation. Okay, you get a relation between those two diagrams look like very, very different. Okay, very, very different. Yes. Exactly, this now standard model is non-zero, and this is exactly what we calculated. We already calculate this. This will give you zero. This will not give you contribution. You should not cut, sorry. You should not cut like this. You should not cut like this because in your basis at the end of the day, okay, you know that this thing, okay, you see, you want to relate here with this thing here, okay? Now, of course, I'm not looking anymore here. I know that this coefficient, when I do the cut, I have a relation. I'm looking at this thing. This is the part I want to calculate, okay? Because this formula gave me the relation, okay? This is saying, I don't know what is this and this, but if I cut, okay, the only thing, if I cut, I mean, I put on shell 2 of them, this will give me 0, and I get this contribution, I get the contribution from here, that I know what it is. It's just taking this integral and putting 2 of these propagators, replacing by a delta function. Okay, so I know what it is, and this I know what it is. This is what I want to get. This is what gives me the anomalous dimension. Okay, and this makes the relation. Now, okay, see, there is no contribution here from only one. The bubble, it's called massless bubble, is 0. This integral is 0. Okay. Yeah, sorry. In this integral, I have the integration, but I have also the momentum of the external. Okay, there is no body coming inside here. Momentum. There is no momentum. There is momentum. There is no invariant Lorentz invariant guy because it's p squared 0. Okay, you need to have 2, and now you have p1 over times p2. Okay, you have p1 over p2. If you have p squared 0, there's no Lorentz invariant term. Integral has to be written as a term of Lorentz invariant, p1, p2, products of them. Here, the only one I have is p squared, that is 0 because it's massless. This is why we call it massless bubble, okay? The one that you, okay, so this I2 of this bubble, this contribution is, this is 0, okay? So this is telling me don't cut 1, okay? Don't cut 1, okay, because you don't need to do it, okay? This is not given to you, this is not, in your formula, you don't cut 1, okay? Cut 2 lines. Yeah, it's a kind of detail, okay? It's kind of detail, but it's important because simplify your life. Because if you cut 1, you have many. And now you start, oh, I have, you see, here it's quite simple, I have to cut. Especially for the renormalization, for this kind of diagram. It's very simple always to find this. I cannot cut this, I cannot cut like this, I only can cut like this, okay? And usually there is 1, but not always. Not always. Now in the nodes, you will see how to exactly calculate it on shell, because I only tell you this is the formula. You see how to do it in the nodes. You will see that really this amplitude we already had. Have to plug it. This already is a three level amplitude. Okay, so it's just a contact interaction. Okay, so already we have it, of course, because a contact interaction. Sorry, the standard mode is here, you plug it here, the calculation, the only difficult part was this. We did it, we put it here, you put it here, and you have to integrate the ellipse. Okay, you put it in with the spin or helicity, you contract this thing, and you get a easy integration, usually it's a cosinus integration, and you get a number, okay? That it shows how to get the final numbers with the eyes and all the details, okay? So when you want to get that is non-zero, of course, you have to be careful, and this is why all these conventions, sorry, if I don't put it perfect, it's in the notes, okay? At some point I accelerated to get to the point that the key point is people found a method, okay? It's not simple now to extend it to 2 loops and to continue, but the idea is find a method at which you can reduce your loop integrals into 3-level amplitudes, okay? Because I don't have on-shell amplitudes is important. Okay, when I know a loops correspond to off-shell processes, and the idea is this, okay, to relate it with, with the amplitude by putting particles on shell. Okay, and doing it on the left-hand side and also on the right-hand side, okay. To-loop becomes more complicated, and it could be shown that a formula like this exists. Formula like this also exists at the 2-loop level, and there's a nice paper with showing that I don't have here, showing that this can go beyond loop order for the anomalous dimension only. Okay, for the anomalous dimension, this can go. The problem is, of course, if I go to 2 loops, the thing becomes complicated, and this is what people are doing. Okay, because if I do loops, to loop like this, okay. Now if I cut it like this, okay, on one side I have 1 loop, okay. On the other side is easy, is a contact, okay, it's a contact term. On the other side is a 1 loop amplitude. And this is why but people, this is the way the people calculate higher loops, okay, doing these techniques a little bit, okay. You see, there are some details here to see, but this is the idea. If I can relate this amplitude by cutting here, by calculating the part coming from the on-shell, putting this diecast on shell, okay, now one side will be a 1 loop amplitude times a 3-level amplitude, okay. If I already calculated all 1 loop, first I have to go 3-level, okay, because I'm plugging here 3-level things. When I have all 3-level, I have to calculate. I calculate the loop. When I have loop, I have to calculate 2 loops. Okay, so the idea goes like this: I have the loop now, and calculate these 2 loops. Okay. Now the relation of this cut with the information of the, I don't know, in the anomalous dimension is still possible to do this kind of things. Okay, formula like this exists. Okay, where you have to cut 2 lines. Okay, you cut 2 lines, sometimes 3 lines. Okay, but you have 2 amplitudes. Okay, sometimes you have to cut 2 lines, sometimes 3 lines. Okay, so the formula becomes a little bit more elaborated. Okay, and you relate this thing with the anomalous dimensions. Okay. Eh? This only gives me the divergent part, yes. If you want to calculate the C4, C3, the other coefficients, okay, as I said, you have to do 3 cats, 4 cats, 3 keys. This is easy. This is the monster. Okay, this is the monster to calculate this. Okay, I can tell you because I have calculated also this term, but it requires another thing. Okay. You see, it's a question of how I can calculate. You have to think a way to calculate it on SHA. Now this is the point. Okay. It could look more complicated to you than doing in Feynman, but I'm saying these days people realize that this is even easier because than doing one from Feynman. The formulas that come with Feynman becomes too many complicated diagrams, okay, to add, and still these techniques are useful. Okay, I cannot tell you how they go because I never went through 2-3 loops calculation. Okay, but this is a.
Hello. Yeah. Sorry. Can you hear me? Yeah. For obtaining the finite piece, like the beyond the pole part, if we want to find the epsilon 0, epsilon 1, epsilon squared pieces, would we need to incorporate the 5-point functions as well?
The finite pieces, you mean here, if I can classify like this. So finite pieces, you mean those coming from, this I can calculate these guys. Okay? You can calculate the C part. This part, you mean? You mean, okay, so sorry, what do you mean by finite pieces, exactly? Yeah, this is the only one divergent. This you can call finite pieces because this is the only one divergent. So by power counting, it's integral of, you have an integral with 2 propagators. Divergent, these are convergent, 3 propagators. The convergent, there are more downstairs, there are more pieces downstairs than upstairs. So this you can do it by 3 cats, 4 cats. Okay, these finite pieces, these are finite, if you call finite pieces. Other thing more interesting, okay, that I have also worked and you can elaborate is if you integrate particles, heavy particles. Okay, let's say you want to integrate, as you do, you have an effective field theory and you say, oh, there are massive particles, and I want to integrate and understand this. You do it, you have done it probably thousands of times. What is the contribution to the dipole operator? Okay, from a heavy particle. Okay, those things, surprisingly, for heavy particles, you can calculate also from cats easily. Okay, because for some reason, I cannot tell you, the rational terms cancel, and they're relatively very easy to calculate. We went through these calculations. Okay, for example, because again, somebody was a paper, Karen Hammett and company were calculating that depend on the theory of massive fermions, there were no contribution, 0 contribution. They were calculating 0 contribution. And we wanted to show that from the cats, you can calculate it, and it's again something not related like this, that the amplitude was 0, but there was a symmetry between the. How what? Okay, yeah, first there is some complication first that I tell you can do it, but there is a first complication is I did all these things for massless particle because the idea that the P, these spinors, okay, I was saying the momentum can be written as spinors, okay, this, I could do it because the determinant of the P that I wrote as a matrix 2 by 2 was 0. Now, the determinant of P going to 0 means related with the for momentum P squared going to 0. Okay, massless particle. If it's not, I have to introduce 2 types of spinors. Okay, so P has to be written as 2 types of spinors. Combination of 2 types of spinors. Okay. becoming to be a little bit more complicated. Okay, there's people elaborating this formalism of a spinor for massive particles. There is elaboration. There's a paper, Yutin Huang and Kenny Hamed, and these people originally, and many other people. Becomes a little bit. This is still interesting, okay, but a little bit more elaborated for massive particles. And you will need, if you have loops with different particles, masses and massless. The best is when, okay, the most powerful the method is when particles are massless, okay? The more masses you put, okay, so you're telling you how complicated, the more masses you put, more complicated. Because you lose this nice property I was telling you how to calculate level things, okay? This you start losing, the theory is very constraining, as I show you, for massless particles. Spin 3 you cannot do, spin 2 is very fixed by this. For massless particles, Lorentz invariance tells you a lot. For massive particles, Lorentz invariance tells you little. Yes. Because somebody showed it, it's a paper that shows that there's still any loop order, you can split it in a product of two, not 3 level 1. I cannot tell you, but people calculate 2 loops, 3 loops, 4 loops, 5 loops, okay? There is some people calculating in some certain theories. The question, you have to find the different techniques, like this one I found for 1 loop, okay? Higher loop, I'm saying. I don't know why it works. I don't know why, I mean, I know it works because you derive it, but I don't know. Usually the divergent part is easier than the final pieces. Even when you do, as Rodrigo was telling you today to calculate the divergent part, it's easier because the momentum, you don't care about the momentum. Simplified, even for Rodrigo, it was simple to calculate by Feynman, the divergent part. As I'm saying, this is derived for massless. This formula is that a higher loop order still works, is derived for massless guy. Yeah, because anomalous dimension, the good thing usually is you can take, when you calculate the anomalous dimension, you can take even in the standard model, you calculate how the coefficient of the standard model runs, okay? The coupling runs, okay? They don't depend on the masses, okay? There is coupling running, okay? You can take usually you take the particles massless, okay? Even though you know them W. If you go to high energies, okay, you want to see the running high energies, okay, usually. Because what is this? This is the running, in some sense, of the effective field theory, okay? So usually you are considering high energy with respect to the mass of the particles. This is the approximation that works and works very well. Yes, yes, yes. Yeah. This can be done also this formula can be used also. Okay, this formula can be used with some care yeah, I didn't give you the reference, but if you look at my papers, I gave the reference. Okay, the third paper I gave you the first day. Okay, there is the reference to the paper that derived this. We derived this formula for 1 loop. The guys derived the formula for any loop of the anomalous dimension and for any theory. Okay, my interest was the normalization of operators 1 over lambda square, what they call it here, BSM, okay, 1 over lambda square. But you can do it, yes. You could do it there, yeah. Because the beta function, this thing, gamma function, beta function in the standard model, also you calculate it, putting the masses to 0. Usually when you calculate, you put the masses to 0. Sorry, which case? This case? The case that we discussed, that there is one like this, the Higgs exchange. Yeah, this is the standard model. This amplitude is the standard model amplitude. This is non-zero and is the only one that you can put minus, total is -2. No, everybody here is massless. Consider everybody is massless. Now, if it's mass, it's a different game. Okay, massless. I consider particle as like a scattering of this very high energy. Well, in this case, it will not change much. I think it's massive. No, this is, yes, depends how you say you're telling me about the Lagrangian at the Lagrangian level. If you integrate it in the Lagrangian level, yeah, this would be this would be this. The only thing here, remember that you with the use, with the Higgs, you use this tilde. I don't know if you use the notation. You contract with the epsilon. Okay, SU2 will contract the standard model. The SU2 here appear different because you have to conjugate the Higgs. So I don't know if you remember the standard model. You can write it like this, okay? But when you do the up sector, the Higgs, you have to take complex conjugate, and now you have to contract the doublets with the epsilon tensor. Here is contracted with the AB delta AB, the doublet, and that is contracted with the epsilon. This is a very crucial point. But okay, yes. Now if you integrate this guy, yes, you got this square. Yeah, this is the guy. Yes. If you integrate the Higgs, because the Higgs is massive, let's say, you will get this, yeah, times this, no? Because you just, something like this would be, this times this, yes. This is when you go to on shell, when you go to licities, this is the minus. Yes. I never like this basis because it's really confusing. the Warsaw base is kind of confusing. I forgot which one because I mix. The Warsaw basis to me mix things. Okay, this is why I never like it. Okay, but we can look at if you want, we can look at this basis how. I mean, it correspond to this, but I think this to me correspond this because it's exactly what you said. I can like integrate the Higgs. Eh? This is a Yukawa here, yeah. Eh? Okay. No. Okay, yes, massless. Okay, thank you also, guys. Okay, it's been a pleasure. So, okay, any question you can ask me, and I hope my intention was a little bit to see. Oh, there is a lot of things to learn here. Okay, it's a different way. Probably, remember, probably this mountain was too high at the beginning for you, some of you, and you couldn't climb it. But don't worry, someday you'll have time and look at this because you learn in a very different way. I think today quantum field theorists. Okay, even myself, quantum field theories, of course, I do quantum field theory, but any quantum field theorist should know a little bit on these on-shell methods, okay? Because it's a different way to see, probably seeing the same way, but the same thing, but from different perspectives. That is what we like so much in science, okay? So thank you for.